Okay, so now let's go over the proof of the fourth statement here. Now there's two cases to deal with. So there's the case that the echelon form matrix is non-singular, and there's the case that it's singular. So let's deal with the case that it's singular first. So if it is singular, then that means we're going to have a zero row in the echelon form matrix. Thus, it will have as a zero, it'll have a zero in the diagonal or on the diagonal, right? Because if there's a zero row, then obviously one of those entries will be on the diagonal, which will be zero. And the product of all of those numbers will be zero because of that zero, okay? And that's the zero product principle in action. And so therefore, this matrix's determinant is the product down its diagonal, because again, we know that if it has a zero row, the determinant has to be zero. So therefore, it works out that way. So that case works. Now let's do the other case where the determinant, or excuse me, where the echelon matrix is non-singular. Well, if it's non-singular, guess what? Then none of its diagonal entries are zero. Okay? And this means that we can divide those entries by a number. And we could use condition 3 in the definition, right? We could use condition 3 to multiply by a scalar to get all of those diagonals to be 1. Okay? So again, this is an echelon form. So if we divide all of those rows, right, we'll get ones along the diagonal, and then we can use the Jordan part of the Gauss-Jordan method to eliminate all of the other entries above the diagonal. And then what do we end up with? We end up with the identity matrix with which has all ones, and therefore, if we do the product of the diagonal, it will equal the determinant. So in both cases, it works. And that ends the proof.